Hello, in this video I will be discussing resonance structures and how you draw them, what they are, the importance of resonance structures, how you recognize them, and so on. First of all, what are resonance structures? Well, from a practical point of view, they are two or more good Lewis dot structures where the term good is kind of relative, but basically Lewis dot structures that follow the rules where electrons are arranged differently, but the skeleton remains the same. Now notice that, and this is very important, that the atoms have to remain fixed in space. So when you draw two structures or more Lewis dot structures for the same skeleton, but where electrons are arranged differently, those are what we call resonance structures. For practical purposes, they are an attempt to represent the bonding in a molecule as accurately as possible, where in some cases, for example, a single structure doesn't work to realistically represent the bonding, and so that's why we need sometimes more than one structure, and those are what are called resonance structures. Do all molecules have resonance structures? Absolutely not. Only in certain cases will they apply, and you'll learn to recognize when they do and when they don't. For example, there's an ion called the cyanate ion, OCN negative. This is not one that you learned in general chemistry among the polyatomic ions, but it is a polyatomic ion, fairly common. It's called cyanate. It's one oxygen, one carbon, and one nitrogen, arranged as you see here, oxygen, then carbon, then nitrogen. That's the skeleton for the cyanate ion. And what I've done here is drawn a resonance structure for that ion. Notice each atom has an octet. The oxygen has its total of 8, carbon has a total of 8, nitrogen has a total of 8. Oxygen has its proper valence, 1, 2, 3, 4, 5, 6 electrons. Carbon has its proper valence, 1, 2, 3, 4 electrons, and nitrogen has 1, 2, 3, 4, 5, 6, which is one more than it should have, so it has a -1 formal charge, and thus the negative charge on the cyanate ion. Here's another possible resonance structure for the cyanate ion. First of all, notice that the skeleton is the same. That one, oxygen, then carbon, then nitrogen, all drawn in a straight line. That one, oxygen, carbon, nitrogen, all drawn in a straight line. Notice that the oxygen has a total of 8 for its octet rule, carbon has a total of 8 for its octet rule, nitrogen has a total of 8 for its octet rule, oxygen has a valence of 7 in this structure. It's only supposed to be 6, so that's where the -1 formal charge comes in. The carbon has 4 valence electrons, which it should, and the nitrogen has 5 valence electrons, which it should. So here are two equally good Lewis dot structures for the cyanate ion. And we might ask which one is correct, and the answer is they both are. And so these constitute what are called resonance structures. Notice this kind of arrow with a single line and two heads, one on each end, is reserved exclusively for resonance structures. This is not an equilibrium arrow where you have two arrows, one pointing to the left and one pointing to the right. In an equilibrium, the molecules are going back and forth between the two states. In a resonance structure, they are not. In a resonance structure, they are both at the same time, and that's a very important concept. So different kind of arrow. Now, why do we need two different structures for this ion? Wouldn't one of them be fine? And the answer is no. Either one explains the structure of cyanate by itself. So what's the deal here? Are there two different kinds of cyanate ions, or why are there two different structures? Well, the answer is both. Actual cyanate ions have both structures at the same time, as I've implied. Now, it may seem hard to believe that it can be both things at the same time, but it's in fact a hybrid of these. It's an average of the two. You might try crossing your eyes and seeing if you can make the two overlap with each other. And that's kind of like what the hybrid would look. Now notice, if it's going to be a hybrid of both two, or in some cases more than two, resonance structures at the same time, then the atoms have to remain in the same place, because if the atoms are moving, then it can't be both at the same time. So here's some facts about the cyanate ion. The carbon-oxygen bond is slightly longer than the carbon-nitrogen. So what does that mean? Well, notice that in this resonance structure, the two bonds would be about the same length because they're both double bonds. In this structure, the oxygen bond to the carbon would be considerably longer than the nitrogen bond to the carbon, because generally single bonds are longer. Double bonds are in the middle, and triple bonds are shorter. So this would have one very short and one very long bond. This would have two equal length bonds. In fact, the carbon-oxygen bond is slightly longer than the carbon-nitrogen bond, but not much. And that's because it's actually a hybrid of these two. So this bond between the carbon and the oxygen is sort of like a double bond. It's sort of like a single bond. It's sort of, we might even call it a bond and a half. This bond between the carbon and the nitrogen is sort of like a double bond, sort of like a triple bond. We might call it 2.5 bonds. And so you'd expect this bond to be slightly longer than this bond. Also, here's another fact. The negative charge in the cyanate ion doesn't really reside on the nitrogen exclusively, nor does it reside on the oxygen exclusively. If you measure where the negative charge is in this molecule, it's actually somewhat on the oxygen and somewhat on the nitrogen. It's sort of spread out. So here's an attempt to draw both of the resonance structures at the same time. This is what's called a hybrid drawing. Notice that the carbon-oxygen bond in one of the resonance structures is a double bond, and in the other resonance structure is a single bond. Here we've drawn as a bond and a half, sort of a complete bond for the single bond, and then another partial bond for the second bond. It's a double bond. Similarly, the carbon-nitrogen bond is a double bond in this structure and a triple bond in this structure. So we draw it as sort of 2.5 bonds, halfway between a double and a triple bond. Then the charges, in one resonance structure, the negative is on the nitrogen. In the other resonance structure, the negative is on the oxygen. So in the hybrid, it's partially on the nitrogen and partially on the oxygen. That little symbol is a delta, meaning partial, just like in a partial derivative in calculus, but this is a partial negative on the oxygen and a partial negative on the nitrogen. Again, it's very important that if the hybrid is to be valid, then the atoms have to stay in the same place. You can't have them moving between one resonance structure and the other resonance structure. They have to be fixed in space or locked into place. Another example, this is the carbonate ion. Carbonate, if you remember from general chemistry, was CO3 with a -2. Well, this is a perfectly fine Lewis dot structure for carbonate. Notice that every atom has an octet. Every atom has its correct valence, except this oxygen has one more than it should, so it's got a -1 formal charge. This atom has one more than it should, so it has a -1 formal charge. So this is a fine Lewis dot structure. But notice we can draw another fine Lewis dot structure in which the atoms are still in the exact same place. I haven't moved any oxygens or carbons, but I've shifted the double bond down to here, and I've shifted a pair of electrons up to there. So this is another fine Lewis dot structure for the same ion. And this also, double bond is in the third possible position over here. So 3 good resonance structures for the same molecule with the atoms in the same places. But you might say, but Dr. Armstrong, aren't these really all the same? Or at least the last two, isn't this just that same thing, just flipped upside down like a pancake? And the answer is, yes, that's true. But in order to do that, you'd have to move atoms. You'd have to pick it up off the paper, turn it upside down, put it back on the paper like a pancake. And remember the rules of resonance structures. I've said it several times, you cannot move atoms, and that includes picking up the whole molecule and turning it around. You have to keep it frozen in space, because what we're really looking for is where can the electrons be if the atoms are frozen in space. The double bond electrons could be here, or they could be here, or they could be here. And in fact, they are all three at the same time. Because the electrons are in different places, they are not the same resonance structure. But it's important to notice that for that to be true, we have to keep the atoms in the same places. Now, what are some facts about the carbonate ion? Well, first of all, it can be measured. All 3 bonds in the carbonate ion are exactly the same as each other. Now, that's not reflected in this resonance structure by itself, because obviously these 2 are different from that one. It's not reflected in this resonance structure, nor is it reflected in this resonance structure. But if you take all 3 of them and put on top of each other, or cross your eyes and make them merge into one, then in fact all 3 bonds become the same, because this bond, for example, is a single bond in this structure, a single bond in this structure, and a double bond in that structure. So it's sort of 2 parts single and 1 part double bond. This is a double bond in this one, a single bond in this one, and a single bond in this one. So again, 2 parts single and 1 part double. This one is a single bond in this one, a double bond in this one, a single bond in this one. So again, 2 part single and 1 part double bond. So they become all the same as each other if we consider all 3 resonance structures. Furthermore, another fact about the carbonate ion, the 3 oxygens all have the same amount of negative charge on them. It's not true in any one of these structures, but if you look at all 3 of them at the same time, they each have 2/3 of a negative charge. And so the charge becomes equally spread out over the 3 oxygens. In other words, the carbonate ion can be represented by a hybrid. I would ask you to try drawing it now using the same technique as I did a few minutes ago, using dotted lines for partial bonds. Also notice that in the example we did a few minutes ago, we did not include the lone pairs because it's very difficult to do. We did include charges, but we put a partial in front of any negative charge that wasn't a complete full negative charge. So if you want to stop the video and see if you can draw a hybrid for the carbonate ion, now here's what it should look like. Notice that it has the exact same location of the atoms. I haven't moved any oxygens or carbons, but this bond being partially double and partially single, I've drawn as a single bond plus a broken line for the rest of the partial double bond. Same thing here, and then it becomes more obvious that the three bonds are the same as each other. Furthermore, partial negative on this oxygen, partial negative on this oxygen, partial negative on that oxygen shows that, that the charge is spread out equally among the three oxygens. Again, not shown that way in any of the individual resonance structures, but taken as a whole, that's how the molecule would look. Now, here's an important idea. Could these resonance structures be drawn upside down or sideways or in any other arrangement? And the answer is yes. It's perfectly possible to draw it sideways like this, or upside down like an actual T-shaped, or many different ways. But it's really important to realize that once you draw one of them that way, you have to draw the rest of them that way. So this set of three resonance structures is exactly the same as this set of three resonance structures. Or for that matter, this set of three resonance structures. Now this is actually more realistic because we know that if you have a carbon with three groups of electrons around it, it's trigonoplanar and the bond angles are 120 degrees. So this set right here reflects that reality in terms of the shape of the molecule. This set does not. But typically when we're drawing resonance structures, we don't really need to draw it realistically in terms of the shape. What we're really looking at is where are the electrons in terms of what kinds of bonds are present and where are the lone pairs present. So this is actually a little bit better way of doing it, but this is actually okay as well. But the key is you have to make sure that when you draw one resonance structure in a particular shape, you have to draw all the rest of the resonance structures in that same shape so that you're not moving any atoms. And that's the key. Now, here's an example. Another example. In the last two cases, we had negative charges involved. In this case, we have a positive charge involved. Notice there are no lone pairs here, but this is the resonance structure of a particular kind of polyatomic ion with a positive charge. One thing you'll notice is that this carbon does not have an octet, but that's okay in this case because there's no way all the atoms are going to have an octet. There just aren't enough electrons in this particular molecule. Now I would ask you to try drawing another resonance structure for this carbocation. Keep in mind that you have to keep the atoms in the same place. So here's a hint. In resonance structures, the atoms have to stay where they are. So try drawing the skeleton without double bonds, triple bonds, lone pairs, or charges like that. Notice that what I did here is drew the atoms in the exact same places, but didn't put the double bond in, didn't put the positive charge in, and then add the electrons and charges back in a different way that still follows the rules as much as possible. Notice that's what I did here. Instead of double bonding that position, I put double bond back in that position over here, and I shifted the positive charge from there over to there. So this is another resonance structure of that same molecule. Notice the atoms are in the same places, but the electrons have moved. Try drawing another resonance structure for this molecule, which is called an amide. Just if you remember looking at the functional groups on a previous video, this is what we call an amide, C double bond O, single bond N. Notice that this is different from the previous examples we've done so far in that it doesn't have any charges. It's no positive or negative. Every atom here is neutral. So take a minute and see if you can draw another resonance structure for this molecule that follows the rules. In fact, the new resonance structure will follow the octet rule. Here's what you should have drawn. Notice what I did as I moved the double bond from this position to this position. I moved this pair of electrons up onto that oxygen. This becomes a single bond, this becomes a double bond, but in so doing, then this oxygen gains an extra electron and gains a -1 formal charge. The nitrogen loses one of its 5 valence electrons. Now it only has 4, so it becomes a positive formal charge. So this is another resonance structure for that molecule. Now, you might say, very legitimately, but this is not as good a resonance structure because it has charge separation, and we always try to avoid charges if we can. This doesn't have any charges, this has a positive and a negative. So what we say is that this resonance structure is not as important of a resonance structure. Is it possible to say this is not as stable as that? Well, you can say it, but it's really not correct because, remember, these are not two different molecules. This molecule has both of these resonance structures at the same time. When you say one is more stable than the other, that implies that one has a different energy than the other. Therefore, it has to be two different molecules. These are not two different molecules. These are both representations of the same molecule at the same time. So the terminology we use is, of these two resonance structures, this is the more important one. This is a less important resonance structure. Nevertheless, even though it doesn't contribute as much to the overall structure of the molecule, it still does affect the properties of the molecule. For example, it turns out that the carbon-nitrogen bond in an amide is a little bit shorter than we would expect for a single bond. That's because it has a little bit of a double bond character in it as well. Also, it turns out that there is restricted rotation around the carbon-nitrogen bond. As you know, single bonds can rotate freely, double bonds cannot rotate. It turns out that in amides, there is restricted rotation around that carbon-nitrogen bond, and that's because it has some double bond character as represented by this resonance structure. Now, here's another important idea about resonance structures, particularly having to do with hybridization. If I ask you to predict what is the hybridization of the nitrogen in an amide, you would look at this structure and you would say, okay, it has 4 groups of electrons around it, therefore it is tetrahedral, and the bond angles should be about 109.5. However, if you look at this one, you'd say, okay, nitrogen has 3 groups of electrons around it, therefore trigonal planar, therefore the angle is 120 degrees. Is it possible for the angle to be both 109.5 and 120 degrees? No, it's not. Why not? Because both structures are in effect at the same time. So it can't be both 120 degrees and 109.5 degrees at the same time. The answer is it's actually sp2 hybridized, and the angle is 120 degrees, in other words, trigonal planar. So this is the one that we use to decide the angles in the molecule in the shape of the nitrogen atom. Why? Well, there's 2 reasons. First of all, we can just follow a rule. And the rule says when you have 2 or more resonance structures that give different answers for the hybridization, different answers for the electron group arrangement, for example, tetrahedral in this case, trigonal planar in this case, we go with the one that has more double bonds or more triple bonds. This obviously has a double bond to the nitrogen, this only has single bonds to the nitrogen, so therefore we use this resonance structure. Even though this is a less important resonance structure, we still use that resonance structure to decide about the shape around the nitrogen. Now, let me just ask you another question. What is hybridization of the oxygen? Is it sp2, as suggested by this, in other words, trigonal planar, or is it sp3, which is tetrahedral, as suggested by this resonance structure? Well, the rule says you go with the one with the more multiple bonds. So since this has a double bond and this has a single bond to the oxygen, we'll go with this structure and we'll decide that the oxygen is also sp2. Now, why is that? It seems weird that you'd use this structure to decide the hybridization of the nitrogen, but you'd use this structure to decide the hybridization of the oxygen. And the answer is it has to do with orbital overlaps and hybridizations, which we will talk about in the next video.